Okay, I think we're good. All right, so this is the whole idea of ensemble learning. Really, all you do is you take a group of models and you create a model with that group. So in this case, we have 3 models, and we're going to look at the prediction of these 3 models. And we're going to use their 3 predictions to make the final prediction. So I'll explain everything in the future slides, but that's the whole general idea. All right. And so the motivation is we want to take a collection of weak models, and together they're gonna be they're gonna work together as a strong model. So it's like the idea of teamwork, right? So here we have instruments, and by themselves the instruments are good, but together they can become very, very powerful and louder and so on. So with ensemble learning, you can mix them with any type of model. So any model that's ever been created, you can use it in ensemble learning. So far we've talked about neural networks a lot, and those are more the new like machine learning models, but there's also classical machine learning models that I haven't covered. I have in like a previous year, but you can find that in the repository. But usually the models that we use in Ensemble is called decision trees. And this is an image of a decision tree where, yes, it's a classical machine learning model, and it pretty much makes a decision at each node. It's like it checks if you meet this criteria or you don't. And at the end is like your prediction. So yeah, they're also very successful in Kaggle competitions. And for those who might not know, Kaggle is it's like a competition for data science problems. So, for example, a organization they might put out a data set, and they have a competition for like X amount of money, and people like amateurs or even teams or even other organizations, they'll build models to work on the data set and try to make accurate predictions and yeah, stuff like that. So a lot of amateur data scientists, they go on Kaggle just to practice, and they also upload their notebooks on there. So I'll quickly like just showcase what it is. So there's a lot of information on Kaggle, and you can also learn by yourself on Kaggle, see what other people do. So here's one, like they're using a convolutional neural network for credit card fraud detection. And so they go very much into detail of what they did and like the problems they've came across and like how they overcome those problems. And then they go through the entire process of exploring the data and then eventually like creating the model. So yeah, that's what Kaggle is. And in a lot of the cases, Kaggle uses ensemble learning techniques. So why do we use ensemble learning? So the whole goal is to create a more robust model. And what do we mean by robust? A more robust model is going to have a better predictive performance. So it's going to be more accurate. It's going to have a low variance, right? And a low bias. So that would be a robust model. So low variance is pretty much like how consistent are you, and bias is like how precise are you, right? So you could have high bias and low variance, so you're consistent, but you miss the target a lot, right? And then in the ideal world, your model should be both having low variance and low bias. So it's going to be consistent and it's going to be very precise. If you have high variance, that means you're kind of like you're inconsistent. So you'll miss the targets a couple times, but sometimes you'll hit it if you have low bias. And then there's like this is the worst case where you're missing and you're not really consistent. Oh, and this is the ideal place. This is where we want to be. And this is the models that this is a robust model. So just to briefly talk about the bias variance trade-off, which is one of the key concepts in machine learning. It's the whole idea of we want to find a model that has, like I said, low variance and low bias, right? So the model should be here, right? We want this is going to be the lowest bias and also the lowest variance, right? So this is the validation error on the validation set. And then this is the training error, which is on the training set. And so this axis is model complexity. So the more complex your model gets, usually the higher the variance. And so this is what high variance looks like. This is the whole idea of overfitting, where the model is it's fitting too close to the training data, and the opposite of that is underfitting, where the model is like it's not fitting enough, where you can see it just has a straight line through all the data points. So it's just like pretty much it's predicting the average of this data. And in the optimal world, in the ideal world, we want a model that can fit the general pattern of this data, but not too much, because if you fit it too much, it's going to be bouncing between each data point. And if we throw a testing data point in here, it's not going to be exactly on that line, right? So this is the whole idea of good balance. And so usually, yeah, usually if the bias increases, yeah, your error will increase, and the variance increases, your error increase. So this is the optimal spot where we have low error and the model complexity is not too high. Okay, so now we'll talk about the techniques. So really, we'll only go over 3 techniques today. So max voting, bagging, and boosting. There are a bunch of other techniques out there, and I honestly don't know all of them, but they all have like different use cases. So there's averaging, and there's weighted average, blending, stacking, and pasting. But today we'll go over these 3 in bold. And so what all these do is they look to either change how we use the predictions of our models. So let's say this is a model 1, model 2, and then this is the nth model. So these techniques, they either is a technique to how to use these predictions of the models, or also can change how we train the model. And max voting is this one, and then bagging and boosting would be changing how the model is trained. So let's go over max voting first. So there's two types of max votings. So the first one is hard voting, which is used with classifiers to predict labels. So let's say we're trying to predict like color or something, and we have these 5 classifiers. One's predicting, we have 3 predicting green and like 2 predicting orange, right? So we just take the majority vote, right? So it seems like green is it's more probable that the data point is green, right? So we'll look at the majority, and we see that 3 is the majority here, and we'll predict green. And this is what we call the committee, right? The committee is the collection of models, and the committee's final prediction is the majority vote. So now we go into soft voting, which is when the classifiers are using, they're predicting the probabilities instead. So this will give us a better idea of like how confident is the classifier. So yeah, so it's a little bit better than hard voting, because we can give more, we can value a higher confident, a model that's more confident. And then we can value less models that are lower confident. So let's see, we have two models here, and they're 99% confident this data point is green. And then we have the 3 other models which are saying that the data point is probably green, and like 0.51 is like, it's pretty much 50%, right? But they're still leaning more towards the green. So obviously we will go with the higher confidence models. We do this by just adding their probability. So like 0.99 plus 0.99 is like 1.98, and then you have three 0.51s, which would be like 1.53. So obviously 1.98 is greater than 1.53. So we'll go say and it's orange. So the committee final say is that it's the data point's orange. And so that's soft voting. And in the demonstration, we'll do hard voting. Okay, so now we'll talk about bagging. So bagging is how we actually change how the model trains. And we still look at all the models and look at their final prediction. And you can use it using like max voting and just like averaging. But bagging is also called, well, the proper full name is bootstrap aggregation. And so like the name doesn't really make sense, but I feel like bagging is a more appropriate name, because what bagging is, you put your entire data set. Well, first you split into training and then you're testing, right? So you take your training data set and then you split it and you put it into bags. So you just put it into different bags and you can reuse these data points. So like each data point has some probability of getting into a bag, right? And so this is the idea of sample with replacement. You just you can reuse data points. So you have a bag for each model, right? Each model gets their own bag and they all have equal voting power. And so these are the bags here. They have, they're just data points from the training sample. And so the data is, so this is the whole process. The data is split into bags. And then the data is, each model is trained with their own bag. And then they all make a final prediction as a committee. And that's the whole process. And then of course, we need to make sure the ensemble, the committee is doing well and is predicting well. So we'll throw test data at it and see its accuracy with test data. So that's bagging. And let's talk about why we use bagging. So this one's going back to the whole variance and bias trade-off. So with bagging, all the models are usually a bunch of high variance and low bias predictors. So what is high variance and low bias? High variance means you're not consistent, but you can hit the target a couple times. So you have a good idea of what the target is, but you're not consistent. And so the result of the committee, right? The committee of all the models that trained with their bag data, you'll have a low bias and low variance model. So this is the committee. And so this is what we want in the ideal world. And so this will increase our accuracy with for predicting on the testing data. And so no longer will the model overfit to the data. And so this is I have a quote on the bottom. It says, you're pretty much creating slightly different models and you ensemble together. So each model kind of has like a different view of the data. And they don't have a view on an entire data, just a small portion of it. And then, each portion like overlaps or may overlap with other models portions. So that's bagging. And we'll go into boosting, which is the final technique I'll go over, and then we'll compare and contrast them. So boosting is a little bit different, and it's the idea, the process instead is you're sequentially training a model. So you first train one model, you wait for that model to finish, and then you train the other model. The reason we wait is because that model is going to make some errors on some of the testing data set. And we're going to look at those errors, or sorry, errors on the training data set, actually. So we'll look at those errors and we'll tell the next model, you should focus on these errors. And so it will make its predictions, right? It then learns and it tries to focus on the errors, and then it'll make a prediction. And they'll tell the next model, oh, I messed up on these data points. Can you like take a look at it, and like that will help you become a better model. So that's the whole process. So yeah, it's each model learns from the previous model's mistakes. And at the end, the final model will be most likely the best model. And we can also just use the final model's prediction, or we can use everyone's prediction, all the model prediction, or just select some models that meet some criteria, and we'll use the prediction. And so Well, yeah, the whole why do we use boosting? It's because we want to train a weak model and make it get better. So like we're making the model stronger. Like it's going through some type of training like process. So we're pretty much changing how like the model is trained. Just a bit. We'll prolong the training part. So first off, it starts as a high bias, low variance model. So in bagging, we started as all the models were high variance and low bias, but this time we're having a model with high bias and low variance. So it's low variance. That means it's a very consistent model, but it's way off from the target. And as a result, after boosting, we're going to have a model that's in the ideal world where we have a low bias and low variance. And this will, we pretty much just increased how precise it is. So we moved, usually it was predicting here, and now we moved it to the center. And yeah, the quote for this one is, we're making weak models become stronger. Okay, so we're gonna compare and contrast them. So I'm gonna briefly just cover what they do. So bagging, it's like if we're gonna draw it to like a real world analogy, it's like you have a bunch of friends and they're all cramming for like a project, and you don't have enough time to finish the project by yourself. So you tell one friend, go focus on these concepts, and then the other friend, go focus on these concepts, and then like yourself will go focus on these concepts. So after you guys do your studying for these concepts that you were assigned, you guys come together at the end and you guys finish the project together, or exam or whatever. Whereas boosting it's like the idea of passing down your knowledge to the next person. So like, let's say the first like CS major that ever graduated from Virginia Tech, they made the mistake of not starting their projects early. So they tell their junior friend, go start your projects early. Make sure you start your projects early for your senior year. So they go ahead and they do that, and they become a senior. And then they tell their junior friend, make sure you apply for like internships. And then that person applies for internships, hopefully. And then they go ahead and become a senior and tell their junior friend advice. So that's the idea of parallel versus sequential. So parallel, like everyone's working in a distributed manner. So everyone is working at the same time. Sequential is you have to wait until the previous model is finished in order for you to continue. So they're a little bit different. And they also have, like the models are a little bit different with the variance and bias. Like boosting, you're going to have high bias and low variance model. And then you have bagging, which is going to have a high variance and low bias model. So that'll also tell you like when you should use bagging versus boosting based off whether the model you have has high variance or low bias, or if it has high bias and low variance. Okay, so on a side note, boosting is usually the go-to method for everyone because it's very powerful, and one of the most powerful models on Kaggle that's being used is XGBoost, which is a boosting model. So like I said in the beginning, decision trees, I haven't covered it this semester, but it's actually a pretty simple idea too. And that's something you guys can go ahead and look on. Like there's a bunch of videos on YouTube. I think StatQuest provides the math behind decision trees. And decision trees are usually used for most of the ensemble methods or techniques. So random forest is the bagging version. So it's decision trees with bagging. So they're all given different bags of data. And then you have boosting, XGBoost trees, which is the boosting version where they learn from the previous model. And so these are very good for tabular data, which is why they're really widely used in Kaggle. And then I have like a YouTube channel if you guys are interested in the math behind it. I don't usually go too much into the math, but if you're interested, yeah, check that channel out. I'll stop there and check for questions in the chat. Okay, no questions. But if you have questions, like feel free to ask. I'm just gonna show you guys the.
when you said base model is a decision tree, does that mean like the final model that you run the classification on will be decided on a decision tree?
So you're asking about the base model.
Yeah.
So like what is, sorry, I didn't explain what the base model is, but it's a little bit of the terminology. So with these methods, you don't mix up, you only have one type of model. For example, you can have like a neural network, like a specific neural network, or you can have a decision tree, or like a k nearest neighbor model, or like even just a linear regression model. And so what the base model is just that type of model. So if I'm going to use boosting on a base model, it's just pretty much use that model, and we're going to train that model, and then the next model will learn from that model's mistakes. And so what the base model is just pretty much the model we're using, and we're only using one type of model.
Okay, so you can't mix models together. Like,
you can in some cases, like bagging, you can mix them, but boosting, you don't mix them because you're learning from. I haven't seen it being used, like I haven't seen it like being mixed, but boosting usually use one model, and bagging you can use multiple. And so boosting, that's why I said a base model, because bagging you can also just use the same model. So what random forest is, it's a bunch of decision trees. So this is a decision tree, this is a decision tree, and this is a decision tree. And that's why I said the decision tree is the base model.
mhm. Okay,
Is that good? Answers your question?
Mhm.
Okay, cool. Alrighty then, so we'll go to the slides. So I have here the repository, and this has all these slides and the notebooks from the past semester, or this semester. So you can find the slides here, and then in the fall 2020 you have all the notebooks. So we're gonna go to Ensemble Learning, and then we can open it up in Google Colab, which is how we've been doing it. But I did say I was going to code from scratch. So we can code something up from scratch. Let's see how it goes. There's not too much code in this, so feel free to just like run this. But pretty much we're just going to go over a data set on like cancerous cells. So they have I think University of Wisconsin, they did collected data on like a bunch of cells and like some of the features of the cells, like their shape and stuff. And then they indicated whether they have cancer or not. So 0 means no cancer, and 1 means that cell is cancerous. So it seems cool. Like you can figure out if a cell is cancerous by looking at its geometric shape and like other features. But we're gonna use a voting classifier, which takes the majority vote, and then we'll use a bagging. So we bag the data, and then boosting, learning from the previous model's mistakes. So let's do that. Okay. So very first thing I will do is I will import pandas, because pandas is how we store the data in a data frame, and it's very useful. And also, I think usually I do NumPy, but I will probably stay away from NumPy. I don't think I need it, but I need sklearn.datasets, because sklearn, which is one of the most popular machine learning libraries for Python, it has datasets provided. So we go to here, sklearn datasets. You can see that it has a bunch of data sets. So we have iris, which is like about the flowers, and we'll be using the breast cancer. So let's go ahead and create another cell, and we're going to import that data. So sklearn.datasets.load breast cancer. So this is the data set. And then we can take a look here, and like that data set is a JSON. I just want its feature names. feature names. So these are the feature names that we have. And then we also have target names. I think I did like a specific trick, but let's go ahead and throw those data points in a pandas data frame. So features equals panda.DataFrame, and the data equals the data set dot data is the data, right? And then the column names is the data set dot feature names. So this is the features. And now we can go get the targets doing the same thing. But the targets are under here, target. So we specify the data and we specify the name of the data. So data set dot target names. So targets look like this. Oh, I didn't like that. So shape was passed. Oh, so I think what was happening is the data set is providing just zeros and ones in a one array, but like the column names that have two names. Sorry, the feature names. So what we'll do, target names. So target names that have two names, we'll just say it's cancer instead of saying malignant. Yeah, we'll just say it's cancer. So now we should have. They want a array. Okay, so now we have it. Make sure it like has values outside of 0. Okay, that's good. So 0 means it's not cancerous, and 1 means it's a cancerous cell, if I remember correctly. Okay, so one thing I'm going to do is I'm going to combine the features and the targets into one data frame. It just makes it easier. Features and targets. And we'll throw that X1. This will make everything easier. Okay. So there we go. So we have all the features, and then we have the labels. So this is a classification problem. And this would be like a bioinformatics problem where they're trying to predict cancer cells. So, so every time before you start a problem or before you actually train the model, you need to make sure you split the data set into a training part and a testing part. So the training part is only used for training the model, and then the testing part is how we evaluate our model's performance. So we can do that using a very, we can use sklearn again. So they have, from sklearn, they have this model selection, model selection like sublibrary or module. And what model selection does, it does all the work for splitting data set. So I think it's train test split. Don't remember the name. Train test split. And so with train test split, we need to pass in the features, and then we'll pass in the targets. So we're looking for cancer. And then we'll say the size, test size equals 0.25. And yep, that will give us all our data. And so we get our X train and next test. And then we got a Y train and then our Y test. So this is all the features for the training, features for the testing, labels for the training, and then labels for the testing. So let's go ahead and see that works. Awesome. So now we can actually build our committee. So the models we can use any model really. So if you guys want to try out a model, then go ahead and try it out. I'm just going to do decision tree, which is tree, and then there's a k-nearest neighbor model. And then there's the neural network, so which is the multilayer perceptron. And then we'll have the ensemble, and then we're going to use the metrics from sklearn to like make sure to do all the accuracy calculations. Okay, so model one, we'll make that a tree. So sklearn.tree decision tree classifier. And then model 2, we can make that the k nearest neighbor classifier. So k neighbors classifier. And then model 3 equals sklearn, and then we'll make it the multi-layer perceptron. If you guys remember in the beginning, we had the multi-layer perceptron, and that's one of the traditional vanilla neural networks. So with the multi-layer perceptron, we do specify the size. And the activation, usually ReLU is the best, so we'll tell it to use a ReLU. And then, yeah, let's just stick with that. So these are all coming from sklearn. So we can look at, let's say, multi-layer perceptron classifier, and they have documentation on what everything is. So here, we didn't have to specify the hidden layer size, but by default, they'll just give you 100 neurons in one layer. But I wanted to just specify my own. But by default, they do tell you to use ReLU. So we don't actually need this. Okay. And so now we can create our ensemble method, which was the voting. So we use the max vote classifier. And this, I believe it's on sklearn.ensemble. And we specify it as this voting classifier. I'm just going to take a look on sklearn. Okay, here. So you give it a bunch of estimators, which we just created, and then you tell it hard voting or soft voting. So we're using hard voting. So we're just going to take the majority prediction, and then, yeah, that's all we really need to do. So estimators, I think you give it tuples and you say, okay, so the first one is decision tree. That's model 1. And we'll set the second model, this is KNN. That's model 2. And then the third model is a multi-layer perceptron. So that's model 3. Okay, so now we have the max vote model. We just need to train it. So we'll do model vote dot fit, I believe. And we'll give it the features to train on and also the labels for the training. Okay, so the model is done, has been trained. Let's go ahead and get the predictions for that model. So vote model or max vote model dot we'll do predict, and we pass in the test values, the testing data points. And so you get a bunch of predictions for the testing data points. So this is the predictions. And now we can calculate the accuracy, which is like how we defined it. I think mean squared error is the common one. So we'll do voting accuracy equals the max vote, so I think is sklearn dot metrics accuracy score. And you pass in the true values and then the predicted values. So y test is the true values, and then the predictions is that. Okay, so now we have the voting accuracy, and let's see how well it does. So it has a 94% accuracy on all the testing data points, and this is for figuring out if a cell is cancerous or not. So that's pretty good, and yeah, I'm actually surprised like how accurate it was. Let's try out the bagging and boosting. So bagging is a little bit different. So bagging model, we just need to use, we could have used different models, but we're gonna go ahead and just use one model. So sklearn, the ensemble, and then we'll look at bagging classifier. And you tell is looking for the base estimator. So the base estimator, we'll use a neural network. So we'll use model 3. And let's say the number of estimators, it was 10, but I want to have like, let's do 3. Let's just use 3 and see how it compares. So like before, we need to train it. So we'll train this using the bagging model, and then we'll also do the predictions and stuff as well. So I just copy and paste just for sake of time. And then let's say this is the bagging accuracy. All right. So you get 62%, which is not as good, but I'm sure like if you use the decision trees, it'd be better. So let's see how that was. So decision trees are much better. We could also like figure out, like sometimes it works because of the weights initialization, but if we increase the number of estimators to like 11, I'm sure it would be better, much better. Yeah, so 90 is better. They also had a problem with convergence, so they give you a convergence warning. But let's move on to boosting, the final one. So boosting model equals sklearn.ensemble. And we can use, right out the box, they provide boosting model. So there's AdaBoost, which is adaptive boosting, but I'm going to go and use the gradient booster classifier. This is the most powerful one. We could use both, actually. So let's go use both. AdaBoost classifier. Do I need to specify anything with this? Let's see. So base estimator is none. Yeah, let's use a neural network for this one, the multilayer perceptron, model 3. And then gradient boosting, it already knows, it's already using a decision tree in the back end. So we can't tell it to use anything else. All right, and then let's go ahead and train them. So train these. All you do is specify the features that you want to train and the labels. Train both of those. And then we could do our predictions again. So yeah. Okay. So now we got predictions. Make sure we don't copy the variables like that. Okay. 1, 2. Okay, we'll just say 1 and 2, and then we'll print both of them in the bottom. Okay, multi-layer perceptron does not support sample weight. Okay, so what do I just do? Model 2, model 2, model 1. Okay, so you had to use a decision tree, and they have pretty close values. I wonder why. Probably because they're both like decision trees, and in some cases you're gonna run into we're gonna see the same value for different models because they just all predict the same, and that happens sometimes. From my experience, it happens sometimes, and usually it happens with decision trees. But yeah, that's cool. But it seems like the boosting trees were the better one, but just by a couple percent. I think in like the actual in the code notebook I showed, the gradient boosting was like, it was far better than the other ones with a 97% accuracy. I'm sure you can like find the best hyperparameters for 99%. But yeah, that's it. It's pretty quick to get set up with if you use sklearn. So yeah, I hope you guys learned about ensemble learning in this presentation. Is there any questions? Okay, then I'll stop recording, and then I'll talk about the meeting on next